cheap or inexpensive textbooks. I'm sure that you would much prefer spending $900 or $1,000 on textbooks, but in case you're looking for bargains, sometimes the quality of the paper might be a little less, but so what. But these are 4 websites that you might want to take a look at, and you may find that they're pretty inexpensive.
There's one across the street, books, I forgot what it's called. There's one right next to the post office. It's way cheaper, a lot cheaper than the other.
A lot cheaper than the Union or the bookstore? Or
Beat the Bookstore.
Oh, okay. Beat the Bookstore? I like that. Cool. All right. Good. Okay. This is lecture 3. And we're going to be starting into roots of equations. Okay, let's return to the problem of the bungee jumper for a moment. And if you remember the equation from last time, we had the change in velocity or the acceleration dv dt was g minus c sub d over m, then v squared. All right? There is an analytical solution to this that you could look up and in essence verify or confirm the solutions that you're running as far as your numerical method is concerned. Now, if you want to solve for the mass, then how do you do it? Well, one way to do this, obviously, is to subtract v sub t. V is a function of time, with the velocity, from both sides. So what you get then is this expression on the bottom, where I've substituted f of n as a function of mass. That's what I'm going to be after. Okay? Now, what I want to do is to make that function equal to 0. All right? So f of m is 0. So what that means is that I'm going to find the value of m that makes that function equal to 0. All right, does everybody understand? So what does it take to balance out the equation, set it to 0? When I do that, that's called a root. All right, so f of m equal to 0. That's what I'm really after. Okay, there's a number of ways to do this, of course. You can do it graphically. And some of you probably did this some years ago, maybe in junior high or whatever, when you were doing finding roots, although they didn't really call it finding roots then, but you did the eyeball approach. Right? Bracketing, which means that you're doing an initial guess. And then that's under the umbrella of the techniques called interval halving, bisection, where you're taking an estimate, making another estimate, and then halving it, or bisecting it, trying to iterate or converge down to what could be the solution. False position, fixed point iteration, of course, Newton-Raphson. Of the methods, Newton-Raphson is the other really important technique. We will spend time with that next time in the next lecture, because that's a technique. If you notice on the homework, I'm asking you to use interval halving and Newton's method, right? And then the secant method, which is really a variation of Newton's method. All right, now let's assume that we have a drag coefficient of 0.25 kilogram per meter. All right, so, and we have a velocity of 36 meters per second, and we've been falling for 4 seconds of free fall. So what would be the value of m? Right, what's the mass? Having that data. All right, now here is a very simple MATLAB model. For those of you that haven't used MATLAB or can't quite remember, here is a simple 4-line MATLAB code. So you just input the values for C sub D, G, V, and T. Then you set up for spacing, obviously, as a printout. You notice that the equation, f of m, is really setting in there on the 3rd line. And then it's the hyperbolic tangent that shows up. So that's the analytical solution. Right? And then just plot the results. Now, if I want to check the validity of this thing, you know, how accurate is it? Remember, I'm setting that thing equal to 0. So when I do so, and I just say evaluate this expression right here, and if I want to know, well, what would that be? The answer gives me 0.0456. All right, what I'm really after is 0, so I know that I've got some inherent error. Sure.
I'm sorry, sir. What does the second line mean?
Second.
Yes, the MP equals line space.
Okay, in MATLAB?
Yeah, is that like the initial guesses?
Yeah, what you're doing is putting in the bracketing value of 50 and 200. Okay.
Thank you.
All right, now, this thing, that little code, by the way, for those of you that run MATLAB, I would suggest you run that. We will load this up on the website. I just found out Friday that we've got the website now. So we'll roll this stuff up, including the lectures here. They're kind of long, so a lot of megabytes. But anyway, you'll have this stuff available on the web. And so if you actually run that code, type it in, you'll actually produce a plot. And so this shows that M crosses between 140 and 150 kilograms. 140, 150 kilograms. How many pounds is that?
300, 280, 300.
That's kind of big, right? Big guy. Okay. All right, now let's get into bracketing and interval halving here. So you're basically making two initial guesses that are going to bracket the root. All right, so you may come up, who knows what kind of values you want, so you're just going to take an estimate. You guess the first value. All right, so in guessing that first value, obviously you're going to solve for the function f of x. Then you're going to guess the second value. You're going to do the same thing again. All right, now the big thing is f of x of 1 times f of x of 2 less than 0. So here's your little check and balance here through the coding. You select a new interval. All right, you select a new value. This would be x of 3 here. Okay, so then you're going to check, now is that value fx of 3 times fx of 1 less than 0, all right? If it is, then you set x2 equal to x3, all right? If it isn't, then x1 equal to x3. You check for convergence. What do I mean by convergence? All right, it says how close am I getting to the correct answer in my iterations or my guesses as I converge to the solution. So I'm checking the difference between the new value and the previous value. All right, so if it's less than some epsilon value, you notice in the homework that I gave you, I'm using something like 10 to the minus 6. Or is fx of 3 equal to 0? All right, if not, go back to 5. Select a new value, repeat the process again. All right, so that's the steps that you go through in doing this kind of operation. All right, now this is an illustration of some solutions that you can get where you notice in parts A and B, fx of I and fx of u, that's upper and lower. And so this would be the upper and lower bracketing, like 1 and 2. Have the same sign, there will be no roots, or there's an even number of roots within the interval. All right, so you can get more than one root. You have to be careful. Now in B and D, if you notice, the function has different signs at the endpoints. Okay, so that means there's an odd number of roots in the interval. Now, fortunately for you, the codes can actually do this. When you write just very simple lines of code, you can actually have it check for you. And so a lot of it can be quite automated. All right, now there are always a couple of exceptions. You can get multiple roots that occur when the function obviously is tangential to x, so it's got a number of multiple roots that could occur. Although the endpoints could be of opposite sign, right? Plus minus, there's an even number of axis interceptions for the interval, all right? So if you notice on B. Also, the endpoints of opposite sign bracket and even number of roots. So these are little rules of thumb that come out when you're doing this kind of particular technique. All right, now here's an example where, my gosh, what is the value that I'm really looking for? You can actually miss it because the incremental length, see, the search procedure is too large. And so what you're doing is kind of bouncing all over because you have all these solutions sitting on the x-axis. So you go, oh, gee, what have I got? 1, 2, 3, 4, 5, 6, 7, or 8 different values there. So you just, the problems that I give you, it won't be that difficult for you where you get into problems like this, but that's where you have to go to other techniques instead of this particular method. Now the bisection method, it's really a variation of the search method that we were just talking about. The interval is always divided in half where you were doing the incremental search method before. So the location of the root lies in the subinterval where the sign changes. All right, so then that subinterval becomes the interval for the next iteration. It sounds obvious. Nice thing about computing, you can capitalize on the fact that they're stupid and they only remember what they've just done. Unless you have to save it, it's going to say, what did I just do? And so in doing that, it's automatically picked up the latest value. So you can capitalize on that and make your programming and logic very, very simple here. All right, now this is what's called a pseudocode. And in a pseudocode, it's not quite a computer code, but it gives you an idea of the procedure and steps that you would go through in logically thinking out how you would solve this problem with this particular technique. Obviously, guess a first value, kind of like what we did before. Then guess a second value. And obviously, you're solving for fx of 1 and fx of 2. All right, is that product of fx of 1 times fx of 2 less than 0? All right, have the interval between your first x1 value and your second value, x2. Iterate to convergence. All right, set x3 equal to the sum of the two divided by 2. So what you're doing is having this thing, all right? So you're bisecting it. Check the product again for the new value x of 3 times fx of 1. If it's true, if it's less than 0, x2 equal x3. If it's not, then x1 equal to x3. All right, check for convergence again. Obviously return to number 5 if you haven't converged. All right, and the problem that I gave you in doing interval halving, I give you a little hint that it's going to take over 20 iterations to do that. So for those of you that are adamant and trying to do it by hand, I strongly recommend you not do it by hand, because it will take you too long. Let the computer do it. It will only take less than a second or so. All right, let's go back to the bungee jumper and look at an example problem. The root changes sign between 50 and 200 kilograms. Okay, so we're going to take an initial guess. We don't know what it is, so we'll start with 50. We'll assume another guess of 200. All right, so first value 50, second guess 200. x3 is x1 plus x2, so I've got 250 divided by 2 is 125. All right, so I'm going to compute the product f at 50 and f with x of 125, and then I get, you notice, a minus 4.579. Then times 0.409, I get 1.871. All right, so those are the two values of the products. All right, this is greater than 0. Okay, no sign change between the upper and lower bound. So what does that tell me? It says, aha, then I must be located in the upper interval on this thing, between 125 and 200. All right, so I'm going to calculate a new value, x4. So x4 is x3 plus x2 divided by 2. What do I get now? I get 162.5. All right, I go through this process again, calculating the function values at 125 and 162.5. I get then a minus 0.147. What does this mean? I have a sign change. So that says, oh, I've got to go a little lower. So I go 125 plus 162.5 divided by 2, I get 143.75. All right, I'm going to check my error at this level. And it turns out the error between the exact solution, which is 142.73 and 143.75, I get something around 0.709%. So that's not too bad. All right, so I've done that in just several steps, iterations. All right, now here's what happens. This is what's really going on when we go through the process. Here's the first iteration. You guess two values. Right? You're going to say, well, this is what I get, x of r. So they say, well, that's not quite right. So I'll take x of r and x of u. I'll have that again. I get a new value, x of r, setting it here. All right? Likewise, then I go, oh, I might have a sign change, so maybe I'll do this value and that value. I'll have it again. And then between here and here, you see what's happening? You see the sequence as you go through the process. That's what's really going on. All right, now this is the error that's associated with the bisection method. So it's the true value versus the approximate value. And so you see the approximate error tails off like this. All right, this is what happens as far as the true error. Anybody have an idea why this is doing this? Right, it's doing jumps back and forth. And so what you're going to wind up getting is something as you approximate this, as you get closer and closer to the actual value, these sudden jumps and changes in here, these discontinuities will begin to change and narrow, get smaller. So that would be the true approximation error versus these jumps from doing the approximation that you're doing or letting the computer do it. All right, now here again is a pseudocode. if you wanted to use the bisection method. So we just call it a function of bisection, and then start with an iteration count of 0, because this is going to take a number of iterations or procedures that we go through. So this is just an idea of what a pseudocode would look like. So from that, you can take that pseudocode and then you can write your own code. This is one of the things that generally was always done when we were writing in Fortran, or some of you that write in C or C++, you may actually do this, is to sort of step your way through a pseudocode, and then from that pseudocode, you can say, oh, here's what I need to do to actually write the statements that I will be using to do the calculations. All right, for those of you that want to use an M file, so if you wanted to do MATLAB, here's an example. Now, what do the percent signs mean on the left-hand side? Just comments, all right? So here's some comments that we've thrown in for you, so you can go through. We're using a function. Notice the function, x1 times function xu. So you can actually do that calculation as a function and embed it within the code. So the code itself, you see, is not very much at all. It's not very long. That's the nice thing that I like about MATLAB, that you can do for very elegant type solutions with a short amount of coding. Okay, now let's look at a second method called false position. This is also known as linear interpolation. Right? And it's, again, under the family called bracketing methods. So instead of bisecting the interval this way, the root's located by joining fx of 1 and fx of 2, we use a straight line. And so it's a relatively crude approximation, linear, but sometimes it works pretty effectively. All right? Where the straight line intersects the axis, obviously is going to then give you the root, or the estimate of the root. All right? Here's the simple formula that you have. X of the root, right, is equal to x upper minus fx of u divided by the difference between the lower and upper values that you use, and then the difference between lower and upper as far as the x value that you assume. All right, it's a very simple formula. That's the equation for a linear approximation. All right, this is what happens. If the blue line actually denotes the true solution, what you're doing then, a linear approximation between 2 points, fx at x of L and fx of u. And so where the root is obviously where it crosses the x-axis, x of r. The difference here between here and here would be what? What would you call that? The arrow, right? So what I would like to do is to make that as small as I possibly can. I would really like to have a true solution, but sometimes I just can't do it. Okay, let's go back to the bungee jumper once again. So that's the curve that we would follow as far as a true solution based on mass. All right, so where this is crossing 0, right, about 142 kilograms or so. All right, let's use false position to determine the root. Let's see what happens. We guess a value for x1. Let's assume 50. All right, we calculate what the function is, fx of 1. We get a minus 4.5, etc. We guess an upper value, all right? Let's say 200, like we've used in the past. So we calculate the function fx of u, 0.86, all right? We calculate x of r. We plug it into the relation for the linear interpolation, or the little formula that we're using there. So x of r then turns out to be 176.277. All right, so now we're going to calculate the product, fx of 1 times fx of r. And what we get is a minus 2.5. All right, what does that tell us? Positive or negative? What are we going to do? All right, it lies in the first sub-interval. So set xr as the upper limit and xu equal to 176, 0.2773, all right? So xl equal 50, fx of L is minus 4.579. Set x of u is equal to 1.176, right? Calculate the function at x of u. Now we get 0.5661, all right? Calculate x of r. We do use the linear equation, what do we get? We get 162.3828. What has happened? What are we doing here in this procedure?
You brought your incremental solution closer to the actual solution.
Right. So what's happening is that we're converging, all right? So these intervals are shrinking down, and ultimately, if we keep going, we will get the right answer, or the correct answer, but at some point, we want to say, okay, that's close enough. That's what we mean by error criteria, when we're satisfied to say, well, that's close enough, all right? So when is false position not so good? Okay, let's say we want to find the root of this equation, x to the 10th minus 1. And it lies between x equals 0 and 1.3. So what happens? So if we use bisection, and I left off the steps in here, but after 5 iterations, this is what you get. x1 is 0.975, xu 1.05, xr 1.01. What's the error? It's 1.6%. Now, we use false position after 5 iterations. What happens? Notice what has occurred. We've actually gotten less accurate, right? We're now running here about 17.1%. So convergence is much slower using false position. Why is that? Okay, let's take a look at the plot function. Okay, so if we plot out the solutions of this thing as we're trying to converge, what is it that's going on here? What do we notice? Okay, in this particular problem, it's going to be really nasty, right? Because of that x to the 10th value sitting in there. So what's going to happen is that we will get an extremely slow convergence of this thing. Okay, now let's take a look. False position versus bisection. So false positions generally superior to bisection. All right? But you must be careful. There are some situations where that may not be true, like the example we just showed. All right? Always check your results. Substitute the root estimate into the original equation. All right? What is it that the root's going to tell you? If I put in the root value, what does the function equal? 0. All right? That's how you're going to check. All right? False position, remember, is one-sided. As you proceed along with doing your iterations, or the computer is doing this, one of the bracketing points will tend to stay fixed. That's generally what happens. If you have functions that have significant curvature, all right, that can lead to poor convergence. Now, from a basic point of view, why is it that that would lead to poor convergence? Because what was the approximation that we assumed for the interpolation? Linear. What's the minimum equation that it takes to account for curvature? Quadratic. You must go up in order, higher order approximations. All right, now we're going to look at other methods